a predicate is not that different from what we call a proposition. Remember, with a proposition, we say that a proposition is a statement or is a declarative statement that can be classified as either true or false, but not both. So when we come here, we realize that it's also, this one is also saying that this is a statement or a sentence that can either be classified as true or false, but then it depends on the variables involved, right? If we can check it, they say that this is a sentence which involves variables, such that if the variables are replaced by definite objects, which we'll talk about such, then the statement is obtained, meaning that the statement can either be true or false when they say that the statement is obtained. So from here, since we can see that a statement will be obtained in such a case, we are saying that, if I go down, we are saying that we're going to be including, for us to get such statements, we're going to be including what we call an universal quantifier, which we sometimes call for all, for each, or for every. And also we have what we call an existential quantifier, which we call, sometimes we say they exist for some. Usually we use for some. So far we've been using for some when we're doing methods of proofs, when we're assuming K to say that it will exist for some. We use there is. So when we come to these two, we know that based on this, one, we are going to say that, usually here's how I label them. We're going to say that whenever we see this universal quantifier for all, we should know that there's no restriction. Let me erase it. We should know there's no restriction. Whenever we see for all, we should know there's no restriction. No restriction. Meaning that every condition or every element should meet the condition. You said that every element should meet the condition. When we see they exist, this sign, we should always see that at least one or restriction is allowed. Let me say restriction is allowed. You'll see when we come to the statements, what do I mean when I say that that restriction is allowed. One, they exist, we are going to say a restriction is allowed. So now, if we go down, we'll need to know these sets. First, we have what we call a real number. Remember, so these are the sets that we're gonna need to know. Let me just go to the site, then I'll try to enter here and write what we'll need to know. From a predicate site, we'll need to know these sets. We'll need to know what is a real number. So what we know about the real numbers is that now these numbers are numbers from infinity up until infinity. You see, right? Such that, let me just put them like this. These numbers are these numbers such that they are rational numbers and also irrational numbers. You see, right? We have rational numbers and irrational numbers. Remember, with rational numbers, we talk about numbers that can be written in the form of a over b, such that b is not equal to 0 and ab are an element of an integer. You see, right? So in other words, we are saying that also integers can be labeled as a rational number, because once I have a 1, we should know that 1 can also be written in the form of a over b. We can say 1 over 1. You see, right? So these integers are from negative infinity to infinity. or they're like this. Like that, right? Then when we have positive integers, we should know when we talk about positive integers, we're talking about integers from 1 up until infinite. You see, right? Then when we talk about negative integers, here we're talking about integers from -1 up until negative infinity. And when we talk about these ones actually are the same as natural numbers. You see, right? Then when we talk about these non-negative integers, these are the ones from 0 up until infinity. And these are the same thing as having a whole number. You see, right? Which is denoted by NO. So if we can be able to know what these numbers are, then we are good to go. Or how are they expressed? You see, right? You should know how they express. This one of a rational number is those ones which are in the root, the form of root or root of something, which cannot be expressed as a form of a over b. So that's why they are a complement of rational numbers. So, okay, another thing I said, remember I said that if we see this is called a universal quantifier. This is called a universal quantifier. And when we say this, we should know that no restriction is allowed. We'll use this when we are checking those questions. No restriction is allowed, or when we are checking the tutorial. And then when we see this, we know that this is an existential quantifier. And with this one, restriction is allowed. The reason why we're saying restriction is allowed on this one is because when we say that they exist, it's possible that it might be one element that makes the statement to be true. So we're going to focus on that element. You see, right? When we say they exist. So let's now go back. I think we're somewhere here. Yeah, we're somewhere here. If we can check the ones which are given to us here, we have a real number, we have an integer, and we have a natural number, right? So I'll just erase here. I'll just erase this because I've already written them somewhere, right? Yeah, so when we are here, we can see that we are given this example. You can see that we're given this example. Or before we think of the example, we can check how do we read such a statement, right? We can see from here, they say from this side, my pen is off. We can see from here, how do we read this? So first, before you think of reading this, you must know that this will read for all. This sign will read they exist. Now this will be our predicate, right? So we are saying here that for all x in, remember this says that this is an element, or it says that it's found within, or it's a member of, right? So we can say for all x in A, there will exist a y in B, such that this will be true. You say, right, or this will be the case. So that's why here they say that for all x in set A, there is a y in B such that P of xy. You say, right. So this will always read like that. So now I given this example. In the example, they say that they say we should determine whether the statement is true or false, and they say we should justify our answer in each case. So first, let's check this. The question says, first we need to know how to read the question, right? The question says, for all x in z such that minus x will always be in a natural number, or it will always be a natural number. So what they're saying is that if I take any number from z, or all these numbers that I take from z, this will always be true. After when I multiply them by negative, there will always be an element of a natural number. And it says all, meaning there's no restriction. So in other words, if I take a 1 from an integer, such that when I multiply that 1 by negative, this will be an element of a natural number. Is this true? Does this look true? Can I have, is this true? Is one element of an integer such that minus 1, is minus 1 an element of a natural number? Because we have checked there that the natural number are the numbers which are from 1 up until infinity. We say, right. So we realize that this is not true. This will be false. You say that. That's why here we are going to say that this is false. Then we justify our answer. Alright. So we're going to say here. So always it is best, or it is simple when you are using a counterexample. So this is false. In other words, it is simple to disprove than to prove that something is correct, right? So we're going to solve false and say for what? If I take x to be equals to 0. You see? If I take x to be equals to 0, which is an element of if I take x to be equals to 0, which is an element of an integer, we know that negative times 0 will not be an element of a natural number. You say, right. So, but I can just leave it like this and say that for x equals to 0, this will be false. Right. Now, we come here. We are saying that there will always exist some integers such that when I multiply them by negative, there will be an element of a natural number. And this is true, right? Because we are saying there are some. Even if I take minus 1 here, if I multiply minus 1 by negative, I'm going to get the 1, and 1 is a natural number. You say, right? So this will always be true because it says they exist. And remember, I said with they exist, there's always a restriction. Restriction is allowed. So we can just restrict ourselves to say 4. But this occurs, I want us to always include all the possible values. This exists for all the negative numbers for x less than or equals to minus 1. So minus 1. This will always be true. You say, right, for all the values of x less or equals to minus 1, this will always be true. Or for all the negative integers. You say, right, if I take the negative integers, this will always be true. I'm sure we agree with this, right? This is always going to be true. So it means that now we can go to C and check. Let's see. Or first, let's review what they're saying here. The first solution, they're saying that for all x element of an integer, for us to have this, they say that it reads as for every integer x, a negative x is a natural number. We say right now. So we say that since we are interested in the set of all integers, you see here, we are interested in all integers. We are interested in finding out whether the negative of all integers is a natural number or not. But that we know it's not, right? Such a statement is false, since for all positive integers x, negative x will give us negative integers, which is not a natural number. So if I take all the positive integers here, I'm going to get negative numbers, right? And those negative numbers are not an element of a natural number. You see, right? So, for example, here, we're going to just pick one number and say that if x is equal to 2, then this won't be true. You see, right? Or we can try to always include all possible solutions. Let's do this. We can go there. We know here that if I take all the numbers that are x or greater, that are equals to x or greater than that are equals to 0 or greater than 0, I'm always going to get a negative number there, and that one won't be a natural number. Is that right? If I take all these possible values, so we can always try to include all the possible values. So now when we come to b, that's saying that there will exist x element of an integer, which is equals to negative x element of that. It means that it reads as follows. They say there exists an integer x such that the negative x is a natural number, meaning that there are some which are true, right? This is what they're saying. There are some which can be true. And if we check, they say that the statement will be true, since in this case, we are only interested in finding out if there's a particular integer. You said that it can be 1, it can be 2, it can be 3, it doesn't matter how many there are. As long as there's at least one, then this statement will remain true. So they say which is negative, which its negative is natural number. There are infinitely many of such which actually we can restrict ourselves to. You see, right? Restriction is allowed, since their negative is positive and the integers, which is a natural number. So if we take those negative integers here and we multiply them by a negative, we're going to get that we will receive a natural number. So that's why we're saying that this will be true for all the negative integers. Now let's come to C. And with C, we're going to read this as it is presented to us. Now, if we check this here, that's saying that this is for all. So how do we read it? We're saying that for all x in R, there exist y in R, such that when I take x by y, I'm going to get a 1. In other words, here I'm saying that if we let's say this one for all, I gotta remember that this one has to take all numbers, and since it came first, now let me educate you on this one. If for all comes first, it's saying that these ones are always gonna be random numbers. Let's say we get 1, since they exist on the second number, I'm going to be the one to choose here to say, since I got 1, I can just pick 1 over 2, such that when I'm at not 1 over 2, I can just pick 1 also, so that when I multiply them, I get the 1, right? And let's say 2 comes first. I'm going to pick 1 over 2 so that I can get the 1 when I multiply them. You see that? So this one will come randomly. This one will be the one which I'll choose, because I can restrict myself here. As long as you see they exist, you can choose. You see, right? So, but here in this case, I choose after a random number has been generated, because this is the second statement of choosing. You see, right? But on the second one, I first choose, then a random number will be generated. I'm sure we see this. So our reasoning will always be based on the one which made us to have a false statement. I thought, let me plug this. I thought it's plugged. So if we check here, let's look at this statement and let me explain what I was saying. So what I'm saying here is that, let's say, I get we're saying that a random number should come first, right? So let's say a 0 comes, and a 0 is an element of a real number. You see, right? let's say x is equal to 0. Can I choose any number that when I multiply it by a 0, I get a 1? Is it possible? It's not, right? There's no number that I can take from the real numbers that when I multiply it by y, I'll get a 1. This is not true. You see that? So this will be false. So automatically this statement becomes false. This will be false for which one gives us a false? It was this x. When x was 0, we found that we got a false statement. So we'll say for x equals to 0. Right, that one was the only statement there that gave us a false. Now we come here to D, we check. Let's say now we're saying that I should be restricting myself. Right? So if you check here, just I choose it now. I can choose any number. When this one comes, it says for all. It doesn't matter what number I choose. You see right now? Because we know that all the numbers here will always have a unique number, which maybe in this case we can say an inverse. That when I multiply by its own inverse, I'm going to get 1. You see it? But then if a 0 comes, remember a 0 can come here. If a 0 comes, doesn't matter what number I choose. If a 0 comes, and that 0 will be coming from y now. If a 0 comes, then x times y will always give us a 0. It won't give us a 1. We said that also this statement will become false for y equals to 0. You see right? Now we come to this one. They are saying that for all rational numbers, there will always exist some real number such that when I take x plus y, I'm going to get 0. Meaning that when I take that rational number, I add it to this real number that I choose, I'm always going to get a 0. You see right? Which in this case, it is true in this case. And how do we know that it is true? Let's check. Let's say, remember I said that for all will always be a number that will come random. Let's say a 2 comes. Obviously, I can take minus 2 here. They will exist. I can take minus 2. Remember, this one, I'm allowed to restrict myself. I can choose any number I want from these ones off. They exist. I take minus 2. And if I take 2, added with minus 2, I'm going to get a 0. So, how do we solve such questions? For these ones, we are going to solve them like this. Always, questions that always have plus in between or minus, we're just going to solve them like this. So, this will be true for. Now, let's check. If x plus y is equal to 0, we must make one of it subject of the formula here. One of these should be a subject of the formula. And the one that should be a subject of the formula is the one that has they exist. Is the one that is going with they exist. And in this case, between x and y, in this case, between x and y is y that has they exist. It means that I must make y subject the formula. So y is the one that should be subject the formula. So this will be true for all the numbers that y is equal to negative x. It means that if y is 2, the other one should be minus 2. With this, when I add them, I can get a 0. Let's say right there. So this will be true for y equals to negative x. So we come to this one. It says there will always exist some integer such that when I multiply it by a natural number, I'm always going to get a 0. So here I'm restricted to choose that. Let's say I choose x equals to 0. Obviously, any number multiplied by that 0, it will always give us what? Any number multiplied by that 0, it will always give us 0. You see right? So in this case, we are going to say that this will be true for x, equals to 0. You see right? So this will always be true for x equals to 0. So now we come to we say here that we are saying that there will always exist y element of R for all x element of R, such that when I take x plus xy is equal to 8x. So always for questions like this, guys, the ones that have a plus in between, you should always just solve and make substitute the formula the one that has the exists. You see that in this case it's y. So I'm gonna solve and make y substitute the formula and see if it will be true. So let me see. If I solve this, I would factor out x first. I'm gonna get 1 plus y is equal to 8x, and then I don't even have to do this, but it's fine, I can do this, or I could easily take this to the other side. It becomes 7x the other side, but here if I do this, I'm gonna be left with 1 plus y is equal to 8 with this, y will be equal to 7. Right. If y is 7, let's say I decide to choose any number here. I choose y to be equal to 7. It doesn't matter what x is. You see right now? If I choose y to be 7 here, I'm going to have x plus 7x, and then I will have 8x, which is equal to the right hand side. So this statement will always be true. It doesn't matter what x is here from the real numbers. I can say that x will be generated automatically. So it doesn't matter what x will be. So this will always be true. This will be true for y equals to 7. So for the one that has they exist. Now we come to this one. We are saying that for all x elements of a real number, we are always going to have x squared being greater than 7. The question is this true? Let's check. Isn't a 0 an element of a real number? But if I say 0, will it be greater than a 0? Isn't a 1 an element of x? If I say I'm always going to get that it's greater than a 1. No. Is 1 over 2 not an element of a real number? If I say, remember if I say this, I'm going to get 1 over 4. But this does not mean that 1 over 4 is greater than 1 over 2. First of all, you get solutions that do not meet it in this way. So, this will be false. For you try to check, you can try to check a range of these numbers. You see, right? You can try to check a range of these numbers. Maybe it can be x in between -1 and 1. If you have these numbers, if you square them there, let's see if I square -1, I'm going to get a positive 1 here. This one will always be equal. So it means that it should be from 0. This should be from 0. So if we have x from, so even if someone would take some number here, but it's really good to take all the conditions that meet the condition. Is that right? So this will be true for numbers that are within this interval. So all the numbers that are within this interval, they won't be true. If you take 1, you take 0, you take 1 over 2, 1 over 3, 1 over 4, they won't be true for that statement. You see, right? So let's review. If we check, indeed this will be false if x is equal to 0. Remember, if this is 0, there's no number that we can take so that we can multiply with and get 1. 0 times anything will remain as 0. And this one, if y becomes a 0, automatically, if y becomes a 0, there's no number that we can multiply with to get a 1. You say, right? So it will be false for that statement. Then we come here to E. We are saying that this will be true if we solve for the one that has they exist. Remember, the one that has they exist is y. If we solve for y, we get that y is equal to -x. It will always be true for that one. And if we come to this one of G, right? If we check the one of they exist, which is y, and we make it subject to the formula. If we make y subject to the formula, we get 7. Y is equal to 7. So this will always be true for that number. And this is false. You see, you can even pick 1 over 2. If we checked for 1 over 2, if x is equal to 1 over 2, this will always be false. You see, right? And this one, it will be true because we're looking for 0. And if we choose 0 there on z, this one of they exist, we choose x will be equal to 0. All the numbers that will come from y will always give us a 0 if we multiply them by that 0. You see that? So that will be true. If we check, this one was simple, right? Now, let me do this.